In this video, I want to take everything we've learned about inverse functions and apply it to some concrete examples. Real quick before we begin though, I want to give an update regarding my upload schedule. I know I said that I was going to be doing 3 videos a week, but to quote Darth Vader in episode 5, I am altering the deal. Pray I don't alter it any further. Alright, I want to do 2 videos a week instead. 3 videos a week got me burnt out really quickly. So something more realistic, I want to release new videos on Sundays and Wednesdays. That's going to be the goal. Alright, so make sure you subscribed so you never miss a video, and also hit that like button. But anyway, let's get started. Okay, here we go. Example 114. Here we're asked to find the inverse of the function f of x equals x plus 3. The first step to doing this is to replace this f of x with y. Alright, so we have y equals x plus 3. And then what we want to do is swap x and y. Okay? Remember, with inverse functions, the input and the output are swapped. Okay, so we have this equation here. The next thing we need to do is isolate y on the right-hand side. To do that, we can subtract 3 from both sides. And that gives us y on the right-hand side equals x minus 3 on the left-hand side. Then, what I want to do is swap the left and right-hand sides. Okay, so we have y equals x minus 3. And finally, we replace this y with f inverse of x. So this is my inverse function. Okay. Let's take this to the left side of the screen. And let's also do some color coding. I want to make f blue, and I want to make f inverse red. Okay? Let's graph these and see what they look like. The blue function f is given by this line here. Okay, and we can see that the graph of the inverse is a reflection across the line y equals x. Okay? That's how it always works out with inverse functions. If we graph them and they're not reflections across the line y equals x, then we know we did something wrong. Alright? And notice that with these lines, we can plug in any value we want. Okay, so the domain of f and the domain of f inverse is all real numbers, and the range is all real numbers for both functions as well. Okay? Let's move to the next example. Here we're asked to find the inverse of the function f of x equals x cubed minus 1. Okay, so let's do the same thing that we did before and replace that f of x with y for our first step. Y equals x cubed minus 1. And then let's swap x and y. Okay, so we have x equals y cubed minus 1. Then, to isolate y cubed on the right-hand side, let's add 1 to both sides. And that gives us y cubed equals x plus 1. Then we need to undo this exponent, this 3 exponent. So to do that, we're going to take the cube root of both sides. All right, another way you can look at it is that we raise both sides to the power 1 over 3. Okay? So when we do that, we have, on the right-hand side, we have y to the 3 over 3, which is equal to y to the 1, which is just equal to y. All right, so we've successfully isolated y on the right-hand side, and we have it set equal to the cube root of x plus 1. Okay? Let's swap the left and right-hand sides again, because this is how we're used to reading it. Okay? And then, for the final step, we replace the y with f inverse of x. And this is our inverse function. Once again, I want to visualize these functions. So let's take this formula to the left side of the screen. And let's color code it again. F is blue and f inverse is red. And let's plot these functions on the same graph to see what we get. The blue function f is equal to the function x cubed shifted down by 1 unit, right? So the curve looks like this. And the curve representing the inverse is given by this red curve here. And we can see once again that it's a reflection across the line y equals x. So we know we did the algebra correctly. The domain of f is all real numbers, and the range of f is all real numbers. Okay, therefore the domain and range of f inverse, both of those sets are all real numbers. Okay. Moving on. Here we're asked to sketch the graph of f inverse and evaluate f of 6 and f inverse of 2. Okay? So here we have the blue curve f of x, and we already have the line y equals x pictured here. So we know that we're going to be reflecting this swoosh across that line. All right? So we know that f inverse looks like this. It's a swoosh that goes up like this. Okay? So that's what the graph of f inverse looks like. And when we evaluate f of 6, what we can do is just look at the graph and notice that the point 6, 2 is on the graph of f. Okay? So that means if I plug 6 into the function f, it spits out 2, which is the answer to the question that we were looking for. All right? So f of 6 is equal to 2. So that's my first answer. To figure out what f inverse of 2 is, let's take a look at that same point, 6, 2 on the graph of f. All right? And we can recognize that if 6, 2 is on the graph of f, then that means that 2, 6 is going to be on the graph of f inverse. Remember, if a point x, y is on f, then that means that the point y, x is on the graph of f inverse. So the input and output are swapped. All right? But that means that if we plug a 2 into the graph of f inverse, it spits out a 6. So that means that f inverse of 2 is equal to 6. Okay? Let's move on to the next example. Here we're asked to use function composition to verify that f and g are inverse functions. Okay? F is given by this function here, x over 2 plus x, and g is given by this function, 2x over 1 minus x. If f and g are inverse functions, then f of g of x equals x, and g of f of x equals x. All right? We should have both of these equations satisfied. So let's try it out. Let's find out what we get when we plug g of x into the function f. All right? This function composition is difficult. All right, this is a challenging problem. So fasten your seatbelts. Because when we plug g into f, we're going to end up with a big messy expression, and we need to simplify it to see if we end up with x. Okay? So if we plug the red function g into f, we're going to take 2x over 1 minus x and plug it into f. All right? And when we do that, we ask ourselves, what does the function f say to do? It says to take what you're given and put it up here in this fraction, in the numerator of this fraction, and then divide that by 2 plus what you're given. And what we're given here is 2x over 1 minus x. So we're going to plug this red fraction into this slot and into this slot. And this is what we end up with. It's pretty messy, but we know how to simplify complex fractions. Okay, we've done this before. The first thing I want to do to simplify this is just rewrite this 2 as 2 over 1. Okay? And we can see that down here, in the denominator of this fraction, we have some fraction addition happening. So we need to get a common denominator to condense those two fractions into one. Okay? So we're going to multiply 2 over 1 by 1 minus x over 1 minus x in green here. Okay? And that gives us this. All right? Now the denominators are the same, right? Both of these fractions have a denominator of 1 minus x. So we can condense them into one fraction. And it gives us 2 times 1 minus x plus 2x all over 1 minus x. All right, and that is the denominator of our complex fraction. All right, let's hone in on this expression here and get rid of everything else. Okay? So f of g of x is equal to this fraction here, which simplifies to 2x over 1 minus x, whole thing over 2 minus 2x plus 2x over 1 minus x. Okay? And we can see that this 2x and this negative 2x cancel additively. Okay? So that leaves us with this. We're almost there. What we can do next is hone in on this fraction up top, and we can pull an x out. Okay, so we have x times this fraction, 2 over 1 minus x. All right? We haven't changed the numerator, right? We haven't changed this fraction. We're just shifting the format of how we look at it. Okay? Because when we pull an x out, we can see that some cancellation happens, right? We have x times this thing over this thing. These two fractions cancel with each other, and that leaves us with x times 1 over 1. Remember, when things cancel multiplicatively, what's left behind is 1 over 1. All right? And when things cancel additively, what's left over is plus 0. Okay? So x times 1 over 1 is equal to x, which means that f of g of x is equal to x. So that first equation we looked at is satisfied. Okay? Great. Next, to confirm that f and g are inverse functions, we need to check to make sure that g of f of x is equal to x. Okay? So let's take this blue fraction and plug it into the red function g. But what does g say to do? It says to take what you're given and multiply it by 2, and then divide that whole thing by 1 minus what you're given. What we're given here is this blue fraction x over 2 plus x. So when we plug it into the function g, we have 2 times that fraction divided by 1 minus that fraction. Okay? To simplify this, the first thing I want to do is just rewrite this 1 as 1 over 1. Okay? And once again, we can see that in this denominator, we need to get a common denominator among these two fractions that make it up. So we'll multiply 1 over 1 by 2 plus x over 2 plus x. And that gives us this. Now that we have the same denominator for both of these fractions, we can condense them into one fraction, and we get this. Okay? Let's hone in on this expression here and erase everything else. And bring it over here. And then we can notice that this plus x and this minus x are going to cancel additively. So those are gone. And that leaves us with this. Okay, once again, what we can do is pull an x out of this fraction up top here to get this. Okay? And we can see that these two fractions cancel with each other. And that leaves us with x times 1 over 1, which is equal to x. So g of f of x is equal to x. Since both of these equations are satisfied, that means that f and g are inverse functions. Okay? So that's how you can check algebraically to see if two functions are inverses of each other. One other thing we could have done, we could have plotted both of these curves and compared them to verify that they're reflections across the line y equals x. Let's work on one more problem. The circumference c of a circle is a function of the radius r, with the formula given as c of r equals 2 pi r. Express the radius as a function of the circumference. Also, evaluate r of 36 pi and interpret its meaning. Okay. So let's start with this formula. Let's start with this function c of r. c is equal to 2 pi r. Okay? R is the input and c is the output. To get the radius as a function of the circumference, we need to isolate r. Okay? So the first thing we're going to do is divide both sides by 2 pi. And we can see that the 2 pi's cancel on the right-hand side, and that leaves us with r on the right-hand side is equal to c over 2 pi on the left-hand side. Okay? Let's swap the left and right-hand sides to get this. And let's also write this in function notation, right? R is now a function of c. So we get r of c equals c over 2 pi. This is the formula for our new function, r of c. Okay? Next, let's take r of 36 pi and find out what it's equal to. If we plug 36 pi in for c, right, we end up with 36 pi over 2 pi. Okay, that's what this function says to do. It says to take the circumference and divide it by 2 pi. So we'll take 36 pi and divide it by 2 pi, and we can see that the pi's are going to cancel, and that leaves us with 36 over 2, which is equal to 18. So what's the interpretation of this? We plugged 36 pi in for c, and we ended up with 18. So, a circle with a circumference of 36 pi units has a radius of 18 units. That's the meaning of r of 36 pi. Okay? That does it for this video. Thank you for watching, and like and subscribe.